wireless is wireless, right? The data for this comes from one of our Wi-Fi questions project, trying to come up with evidence-based answers and do some experiments to see if we could get answers around Wi-Fi. This question and answer has to do with wireless. We hear wireless all the time. Wireless, wireless, wireless. Yeah, but my wife doesn't understand the difference between cellular and Wi-Fi. You should. Let's talk about some of the differences. First up, cellular has per packet charges, and it's all about ARPU, average revenue per user. They're all about taking money from clients using. I mean, that's their business model. LTE is the current technology we use there. We could go back, all the way to the 1x RTT for data that way. These are always controlled by some central authority, not just the business, but the actual traffic flow is controlled by a cell tower. Now, if you contrast that with Wi-Fi, Wi-Fi is uncontrolled. It's free. Most situations, totally free. It's not driven by any central control. The protocol itself has to figure things out. Now, we call that distributed coordinated function. Now, that sounds really dumb. If it's coordinated, how can I coordinate it by distributing? Well, what it is each of the individual devices, every transmitter, whether AP or client, all have to make a decision on when to transmit and to try not to bother all the other neighbors who are trying to transmit on the same frequency. So there's a big protocol around, we call it the game when we're teaching classes, how a transmitter has to wait for a dead air, then pull a random number, then count down, and then get access and do preamble detect and energy detect and all these things to minimize the amount of collisions that take place, because Wi-Fi is CSMA CA, collision avoidance. We have no collision detection. Thus, Wi-Fi is not very efficient at all. As a steward of the minimum we get of frequency, the spectrum that's been assigned to us, we're not really efficient at using it. LTE, extremely efficient, but they use an entirely different kind of protocol. So to prove this, we're going to do some testing. Let's talk about our testing. In this testing, what we wanted our design goals to be easy, repeatable, and you could do this on your own with any device at all. We wanted a local test server and a remote test server so that we could test the cellular on the other side of a link that's our WAN test, and then test Wi-Fi only, which is our WLAN test. And we wanted anyone to be able to pull this off, so we wanted on any device, both to have local and on the internet. And so what we opted to do was use a WLAN Pi. The WLAN Pi is a little handheld single board computer. And one of the pieces of software that's running on a service is from LibreSpeed, and it's an HTML5 throughput tester. Now later there's a slide that's going to show you all the details that's behind it, but just realize it's going to run a jitter test, a ping test, a download and an upload, and different timing. And if you care, if you're anal and you want to know all the details, they're available for you. And because it runs on lots of platforms, you can run it on Linux or Windows or wherever you want. We just chose to put on WLAN Pis because it's simple and it felt more like a device. That's our target, our end target. And from the client side, all you needed was HTML5, and this runs on any current browser and on mobile browsers even. And it does each of those things I mentioned. So let's look at our test setup. What we did is we were going to test a client. We actually tested 4 different types of clients against 4 different types of access points and then aggregated the data together. On the green path is our WLAN path. Client to AP to a switch directly to the WLAN Pi that's connected to the switch. There was no traffic that went over the WAN. It's all local. The red traffic is our WAN traffic, and it followed the same path. The client device to the access point, to the local switch, but then that switch was connected to a MiFi, a cellular to Ethernet converter that did that little work. By the way, the site we used, there was a cell tower within 100 meters of where we were. So it's very good cell connection. Now in this picture, I called it internet backhaul because you can use this exact same technique to test your backhaul at home, at an office, anywhere you like. One of the devices is to connect only to the AP to give you only wireless, and the other one's going to be placed on the other side of your internet connection, back at your home office. This one happened to be at a school district office. We were on a school district property, and this was in their office. But to get to it, it had to go out over AT&T Cellular, back in from the cellular network, and back into where that was. So that was our test setup. The test tool looks something like this. When you run it, it's going to do a 5-second test on ping and jitter, and it's going to capture some data for ping and jitter information, and you get the little speed dials as it do it, but it also shows a little history of how it happened. And then it goes through a download cycle for 15 seconds and an upload cycle for 15 seconds. So this takes about 30 seconds per test, and we did one test per client against 4 different APs. So each client did 4 APs, next client does 4 APs, etc. So we collected all that data. The graphs I'm going to show you, they were all aggregated back together. We do have the data for the individual ones, but for this demonstration to show the difference between WAN and WLAN, the aggregation was fine. And I promised you the detail slide. Here's the detail slide. We'll give you the slide. I'm not going to read through this. It's just the details of the processes that took place on the Libre Speed engine that we were using. Now, on to the results. In this evidence, again, aggregating 4 clients against 4 access points, the orangish brown are distances across the football field. We went from 10 meters to 25 meters to 50 meters, 75 out to 100. Note the numbers are pretty high here. The WLAN numbers for all devices in aggregate stayed around 60 meg, even all the way out to 100 meters away. So we're doing kind of 2 tests. One test was, what's the difference between cellular and Wi-Fi? Wi-Fi beat the pants off cellular. Even at 60 meg, now I don't know where you live in the world, but I know where I live. I have terrible cellular. If I can get 4 or 5 meg, I'm doing really good. In this test, we pulled about an average of 12 meg across the cellular network. Now that could have been bandwidth limited on AT&T side, but across the board, it stayed flat. Now, think about that for a minute. The wireless LAN was fast, above 100 meg when we were close, and the cellular was kept. We lowered the WLAN, and cellular stayed the same. We lowered the WLAN by going further away, and cellular stayed the same. Now, this would happen as we go further and further and further out, because, the cellular was not our bottleneck. Perhaps maybe if we kept going, maybe the cellular was the bottleneck. Our wireless LAN was not the bottleneck. And at some point, if we kept going, maybe our wireless LAN would drop below the 12, and then the cellular would have matched that. But we didn't go that far. We can use the same technique, the exact same technique, have a Libre server. We happen to be running a WLAN Pi local and one across. So what if you didn't have these? Well, what could I do? You can use this same technique to troubleshoot your Wi-Fi. WLAN alone versus WLAN plus internet backhaul. Those are the 2 things we're going to be testing. Now, the quick way to see this is to check your MCS on your WLAN side. Now, if you have a Mac OS, you just hold the Option key, hit boing, boing, boing. It'll show you the MCS. If you have a Mac, you can also run Adrian's tool to show you what it is. If you're not on a Mac, you might have to look at a data rate, find the data rate, reverse engineer, and look it up on an MCS table. But that will tell you what your MCS is. Well, it doesn't really matter what your MCS is. If your data rate's high, you're getting good throughput through the wireless LAN. If your internet is slow and you have fast Wi-Fi, you don't have a wireless problem. Now, if you don't have the speed test that we used, you can always go out and hit speedtest.net. And now it's going to test your wireless connection, your firewall, all the way back to wherever some Ookla server is, and it'll give you a number. The example here I have was from a hotel I did in Dubai. The number I was getting was 867 on my wireless connection to the AP. MCS 9, I was maxed out. That was as fast as the APs could go. Yeah, my MacBook could have went up to 1.3 gig, but the network was up at 867. Should have been fantastic. But if you look at the speedtest.net numbers, I was only getting 1 meg, less than that on download. I went to the office, talked to the manager, and he goes, "Why is everyone complaining? We spent $100,000 on our new Wi-Fi." I said, "Your Wi-Fi is fantastic. It's your internet backhaul." And he proudly said, "But we have an E1. For those of you who don't do the international stuff, T1 was the US version, and it did about 1.5 meg. E1 did about 2 meg. So they had over 200 hotel rooms, and they were trying to share a 2 meg backhaul. Even after spending hundreds of thousands of dollars on good Wi-Fi, great Wi-Fi. So if you ever need to use this, compare and contrast your wireless connection to your WAN connection to see where it is. Now, final question before I let you go. Will your WAN ever exceed your WLAN? Think about it. Conclusion is, as long as your wireless LAN is exceeding your wired backhaul, Wi-Fi is good. The faster your wireless LAN goes, great. Another conclusion, you can take in free space a client, even an iPhone off of an AP 100 meters away and still be pushing 60 meg. So when people go, well, how far does Wi-Fi go? A long way. Thanks for listening. If you have any other questions, send them on. We'll see if we can answer them in part of this series.